Hello everyone. Let us look at metric spaces and topology today. So in maths, whenever we want to do something, we start with a set. For example, a vector space would be a set. A group is a set. A ring is a set. Everything is a set in maths. But if we want to do like some specific things, if we want to give some specific structures, then we need to add in like more structures to our set to do like more interesting things. So metric spaces is one of them. So a metric space is a set. A set is basically a collection of points, for example, real numbers. But it also has a notion of a distance between 2 points. So an example would be R2, like this is the example, a very standard example that is worthwhile to keep in mind throughout this course. So in R2, we know like there are points in R2. These are a pair of real numbers. And between these 2 points, we have this notion of a Euclidean distance. So between these 2 points, this is a distance, for example, 5 meters. A metric space is a set with some distance. So we'll just try to make this notion more systematic. So we have set, and we have a distance function d. So we normally denote it as x comma d, where x is the metric space and d is the distance function. And this d has to satisfy certain properties, because a distance, say from a place A to place B, a point A to point B, is a non-negative real number. So D should take 2 points next to R, and the distance between 2 points, say A and B, has to be a positive number, non-zero number, and it's only zero when with D of A comma B equals 0, if and only if A equals B. So it's only 0 when the 2 points we're considering the same point. To go from A to A is 0 meters, like it's 0 distance apart. Otherwise, it's some positive number. We also need another axiom. So the distance between A and B should be the same thing as distance between B and A. Distance between B and A. And finally, we want this notion known as triangle inequality. So all it says is that if we have 2 points, say A, B, and C, then suppose we are dealing with like normal, usual sense of distance. So what we are saying is that distance between A and B, so that's like length of this path, in a sense, if we think of the normal standard distance, is smaller than or equal to a distance between A and C plus the distance between B and C. So this guy here is the distance between A and B. This is distance between A and C, and that is distance between B and C. So all we are saying is that distance between 2 points is always less than or equal to distance between each of these points with some other, like some third point, B comma C. This is known as triangle inequality. So as long as we have some set and this distance function that satisfies these 3 properties, we call it a metric space. Some examples of metric spaces? Well, you know real numbers, the thing you've been doing in real analysis. So in real numbers, with the following distance function is called is a metric space. So suppose real numbers with the following distance. So what do I mean by this? A distance between any 2 real numbers A and B, if we define that as absolute value of A minus B, then this would be a metric space. And you can check it satisfies all 3 properties. For this one, let us quickly check this. Is the absolute value always non-negative? Yes, it is. Is it 0 only when a equals b? Yes, because this absolute value of 0 is 0, and a positive or negative number is non-zero. That's a check. Is the distance between a and b same thing as distance between b and a? Yes, that is also true. And finally, is the triangle inequality true? Yes, triangle inequality is also true. And b is less than or equal to minus c plus b minus c. So that's an example of a metric space. Do we have any other examples of metric spaces? We absolutely do. The other one is obviously the example we had in the back of our mind when we were constructing this entire phenomenon, R2, with the Euclidean distance, where, say, distance between, say, 2 points, so x1, x2, and y1, y2 is given by square root of x1 minus y1 square, the usual one, plus x2 minus y2 square. And this is the standard Euclidean distance, or the distance as plane flies. But there are also other distance functions we can put in R2. And let's look at some other distances. Another distance would be a distance between 2 points, say A, B, and C, D, say is equal to like something like this, like a taxi would drive on a road. So let's call this D taxi cab. So I come a D taxi cab. Let's call that D of x1, x2, comma y1, y2 would be equal to, now here it will be the sum of the absolute values of the components, x1 minus y1 plus x2 minus y2. Now the question is, does this satisfy the three properties of metric spaces? If you don't remember, three properties were distance between any 2 points is always greater than or equal to 0, with 0 if and only if p equals q, symmetry, q equal distance between q and p, and finally triangle inequality. So are these three properties satisfied for this kind of metric, R2 with taxi cab distance? If we define the distance between any 2 points to be this taxi cab distance, are these three satisfied? And as you can see, we can check them. The symmetry is obvious because if you just swap x1 and y1 and x2 and y2, none of these are changed, so this isn't changed, so this is fine. The first one, is it always positive? Obviously, we're just adding two numbers, two absolute values. Of course, it is going to be positive. And the only way to make it 0 is to make each one of these 0. But that's same thing as setting x1 equals y1 and x2 equals y2. So that's only when the 2 points are the same. Finally, how about the triangle inequality? Just as an exercise, let's just do the triangle inequality. So one exercise. Let's just do this triangle inequality. So let's say we have 3 points, x1, y1. Let's write it in terms of x1, x2, y1, y2, and z1, z2. And the question is the distance between like these 3 points, does it satisfy the triangle inequality? I'll just put it over here. So what does the triangle inequality say? The triangle inequality says that if you are looking at the distance between any 2 points, say y1, y2, this distance, where we are using the taxi cab distance, it has to be less than or equal to distance between, say, x1, x2 with the other one, the last one, z1, z2, plus the distance of y1, y2. with the last one, z1, z2. Now, this we can just do, let's see how it goes. So where d means a taxi cab distance. So the left-hand side is the sum of the components, the difference between the components, absolute values, plus x2 minus y2. And we want to show it's less than or equal to the distance on the right-hand side. Well, just because we know the triangle inequality holds for absolute values, because these are just real numbers, we can just bring z's in. And the first one is less than or equal to x1 minus z1 plus y1 minus z1. And the second one is less than or equal to x2 minus z2 plus y2 minus z2. And then you just have a look at it. And then you see, you will see it very soon, don't you worry. You see that if you just look at this guy, first two guys, it's precisely the distance between this, x1, x2, and z1, z2, the taxi cab distance we're defining. And the second guy, the sum of these two, is precisely the distance between y and z, so which is what we wanted to show. So it also satisfies the triangle inequality. So R2 with d taxi cab is a metric space. Now I will show you something known as discrete metric. It is not very useful metric when you want to do anything practical. So, like, what's the whole point? The whole point is this metric is always, like, almost always used, like, whenever you want to come up with the counterexamples to metric spaces. So, what's the discrete metric? I could use R2, but I'll just use a random set. Let X be a random set, and D, this metric space, this distance function is defined as follows. So the distance between any 2 points, B, is always equal to 1. So, but we also want that it's equal to 0 when it's between A and itself. So if A is not equal to B, 0 if A equals B. Now, and what it does is it just tells you whether or not two things are the same. If the distance is equal to 1, then the 2 points you are considering are not the same points. If the distance is 0, then it's the same point. Now, it looks like a silly metric to consider. Okay, first of all, is this in the metric space? What about the positivity? Is the distance between any 2 points always positive? Yes. And 0 if and only if A equals B? Yes. It is positive, so positivity is fine. Do we have this property, the symmetric property? Well, if A is not equal to B, then B is not equal to A. So it's either both 1 or both 0. So that's also fine. What about the triangle inequality? Well, is it true that given any point A, B, and C, the distance between A and B is always less than or equal to distance between A and C and the distance between B and C? Well, there's only case work to be done here. Now, if A is the same thing as B, then the left-hand side is equal to 0. If A equals B, distance between A and B is equal to 0. So there's nothing to check. The left-hand side is always equal to 0. The right-hand side is always bigger or equal to 0. So it's obviously going to be bigger or equal to 0 if there's add two numbers that are bigger or equal to 0. So the triangle inequality is satisfied. So in this case, if A equals B, then this is true. So what if A is not equal to B? If A is not equal to B, then left-hand side is equal to 1. But then C can either be equal to A, it can be equal to B, or it can be not equal to anything. So this thing can be 1 or 0. This thing can be 1 or 0. But they can't both be 0 because C can't be equal to A and B because A and B are not equal. So this is always bigger or equal to 1, even when A is not equal to B. If A is not equal to B, then at least one of C or D, B comma C equals 1. So this inequality is satisfied. So any set with discrete metric is a metric space because it satisfies the axioms of a discrete metric of a metric space. Now you might be wondering like why we even consider discrete metric. And the idea is very simple. Because whenever we do metric spaces and topology, we care about continuity, sequences, series, open sets, and closed sets. And we might start making statements like, oh yeah, is the following set closed or is it open? And we will definitely like make the definitions precise on the next video or the session. However, like whenever you need to come up with a counterexample, because like, so I might ask you like, here's a statement about a metric space. Is it true for all metric spaces? Then you would have to either prove it or give me a counterexample. And usually if something looks plausible but maybe it's not quite true, then if you look at discrete metric spaces, then most of the time that will be your standard counterexample for almost all statements. Now it seems like something too magical, but then we will see over time that why that is the case. I will end this video here, and I look forward to seeing you in the future sessions. Bye.